In this video, we're going to look at topic C.1 from the new IB Physics Syllabus. It's on simple harmonic motion, but it's the additional higher level material. And it's really about those two equations that you can see in the top right-hand corner of your screen. So it's all about the equations of motion for simple harmonic motion, and we're going to include what's called the phase angle. So we're looking for the equations of motion for simple harmonic motion. And we're going to start with an analogy between circular motion and simple harmonic motion. So I'd like you to complete this little exercise. I want you to imagine this object moving around in circular motion. And we're going to plot the y component of its circular motion. So the y component would be this here. And at any time, it would have passed through an angle theta, and the radius of the circle is r. So first, what would that y component look like as it passes through one cycle, one revolution? And then secondly, can you write y in terms of r and theta? Well, hopefully you said that the y component starts out at 0. It increases until it reaches a value of r, the radius of the circle. And that's going to be at a quarter of the way around the circle. So if I put this into quarters, it's going to reach a maximum here, where it's at a value of r. It's then going to fall back down to this point, and then it's going to have negative values of y down here until it gets to that minimum value of y. And then it's going to come back and then start the cycle all over again. And then our equation, that's quite easy to do because y is equal to r sine theta. That is, y divided by r is the sine of theta. Y is the opposite side, r is the hypotenuse.
Here's a quick visual that will show you how that works and how that relates to simple harmonic motion. If I press play here, you'll see that the y component is simply following the motion of the mass in simple harmonic motion. And we're getting a sine function.
So we've really got this analogy going between uniform circular motion and simple harmonic motion. And we can say things, for instance, like there's a radius in uniform circular motion. And what it becomes in the simple harmonic motion, what it's analogous to, would be the amplitude, the maximum displacement. And then this vertical displacement that we see in uniform circular motion, it becomes what we'd call the displacement. Usually represent that by an x. The angle in uniform circular motion, well, we could say that that angle is given by the inverse sine of y over r. And we're essentially going to use the same angle in simple harmonic motion, so that theta would equal the inverse sine of x over the amplitude. In terms of time, theta is equal to omega times t. That is the number of radians per second, the angular velocity, times the number of seconds, so that we get an angle in radians. And we're going to do exactly the same thing in simple harmonic motion. So now you'll notice, if we take the case where t is equal to the period, so we've gone through one full cycle, then of course we're expecting that the angle should be 2 pi radians. And we can see that here, because omega is equal to 2 pi over the period. You multiply that by time, and you set the time equal to the period, you're going to get 2 pi times period over period, which is just 2 pi. So this angle that we've rotated through is always equal to omega times t. So we now ask the question, what is the displacement equation of motion for the simple harmonic motion? What's the mathematical equation in time that's going to describe our simple harmonic oscillator? And once again, it's helpful to think of the analogy with the circular motion. And so let's take the simplest case first, and we imagine that at t equal to 0, our object has a displacement of 0. And let's imagine that it's going to rotate in the counterclockwise direction. And then that would be the case that we've been looking at so far. And we just get that familiar sine curve. Something like that. And this here would be the time equal to 1 period. Now, of course, this is a big restriction because we're saying that our simple harmonic motion at t equal to 0 has to be 0. And that's not necessarily going to be the case. So let's imagine that at t equal to 0, the object was here instead and not at 0. And we would have rotated through some angle phi. We're going to call that the phase angle. Our object is starting right here, and then it's going to rotate clockwise. So the curve is going to do something like this. So you'll notice here, when we start with a positive phase angle, we actually shift our curve backwards, that it got shifted to the left. So if our initial curve was just x equals x0 sine omega t, then our new curve with the phase angle phi is going to look the same, except that we've added phi in the argument. This here is called the argument of the sine. So when t equals to 0, we take the sine of phi, which makes perfect sense. Now, how far would it shift backwards here? Well, that just depends. The ratio of the time compared to the period has to be equal to the ratio of phi compared to 2 pi. So the amount we'd shift backwards in time would be phi over 2 pi. In other words, what fraction was phi out of a complete rotation 2 pi times the period. So the amount of shift backwards for a positive phi would be given by phi over 2 pi times the period. So let's look at aligned xt, vt, and at graphs and equations for simple harmonic motion. So let's start with the graph for the simplest case where there's no phase shift. And we're going to start with an object in equilibrium moving to the right, and we get that typical sine curve. Now, if we throw in a phase change, we shift that curve backwards a bit, and it would look something like that. And the equation of that green curve would be x equals x0 sine omega t plus phi, as we just saw. Now, if we do the VT curve, and we'll do the VT curve for the unshifted case first, and of course the slope of an XT graph is equal to the value of the VT graph. So we're going to start off with a strong positive slope, and that means our velocity is large and positive, or maximum and positive. So our curve would look like that if it's unshifted. Of course, if we now shift it, we add phi in our argument and we shift our curve to the left. So our maximum would occur over here somewhere, and everything is going to be a little bit shifted. Something like that. And of course, our curve would have to be v equals v naught, the maximum velocity. We can see that this is a cosine curve, so it would be the cosine of omega t plus phi. Now, we saw earlier that v naught is equal to omega times x naught. So we can replace that v naught to get this equation, v equals omega x naught times the cosine of omega t plus phi. So we can adjust phi there to get any starting position for our oscillator. And we can do the same thing for the AT graph. We could look at the slope of the VT graph, but we know that by the defining equation for simple harmonic motion that A is equal to negative omega squared times x. So A and x always have to be in the opposite direction. So that pink curve, if we make the A in the opposite direction, it's just got to be an inverted version of the xt curve. It's got to look like that. And then if we shift it to the left slightly because of phi, then we're going to get something that looks like that. So now if we just plug into this, A must equal negative omega squared times x. Here is x, x0 sine omega t plus phi. And this is interesting as well because this coefficient out front, the omega squared x naught, that has to be the maximum value of the acceleration. That is, A0 must equal omega squared times the amplitude. So you want to notice here the similarity between these two equations here. If you're asked to find a maximum value for the velocity or a maximum value for the acceleration, the maximum velocity will equal the angular frequency times the amplitude. And similarly, the maximum acceleration will equal the angular frequency squared times the amplitude. Let's try this question. We're being asked for the equations of motion, xt, vt, and at. We want to write the equation as a sine function for the displacement time. It is simple harmonic motion. We're told the amplitude, we're told the frequency, and we're also told that at t equals 0, the displacement is 16 centimeters. In other words, it's at the maximum positive displacement. So let's quickly draw that. So we're doing an x versus t graph. We know the period is 4. I'll break that up into quarters. And we know the amplitude is 16. And we know that it's going to begin at plus 16, and that means the curve has to look like that. So we could write it as a cosine function. That's really a cosine function, but of course we're being asked to write it as a sine function. So we need to figure out the phase angle. So we're seeing how far do we have to shift the sine function. Well, the sine function would look like this. So if I look at the maximums, the positive maximums here, that has to be shifted back by 1/4 of a period. So this is a shift back by t over 4, or 1 second. So our equation in displacement will be equal to, well, the amplitude or maximum displacement. We're told to use a sine. Omega t, well, omega would be 2 pi over the period. And the period is 4. And we multiply that by t. And then we've got to add on the phase angle. So for the phase angle, we're talking about 1/4 of a period, 1/4 of a cycle. So what is 1/4 of a cycle in radians? Well, a full cycle is 2 pi. So we'd like 1/4 of 2 pi, or pi over 2. So we need to add on here pi over 2. So our equation is going to become 16 sine pi over 2 times t plus another pi over 2 for the phase angle. To get the velocity equation, that would equal, well, the maximum velocity. Whenever you have a displacement that's a sine, the velocity will be a cosine. Omega is, of course, the same. The phase angle is the same. And we can write that maximum velocity as equal to the angular frequency times the amplitude. And so that's going to be equal to pi over 2 times 16 cosine, well, pi over 2 t plus pi over 2, and this will come out to be 8 pi. So we get an answer there of 8 pi cosine pi over 2 times t plus pi over 2. So now let's take a look at the acceleration. The acceleration would be negative omega squared times the displacement. So that'll be negative omega squared would be pi over 2 squared. X, we go back up to this full equation, which would be 16 sine pi over 2 times t plus pi over 2. And we can simplify a little bit. We're going to get negative pi squared. 16 over 4 would be times 4. And then we'd have the sine of pi over 2 times t plus pi over 2. So this would be the equation for the acceleration. This is the velocity, and this is the displacement. In this example here, we're going to see the function graphically, and then we've got to come up with the equation. And they want us to rate it as a cosine function. So pause the video, try the question, come back for the answer. So you probably started by noticing that the maximum velocity is 5 meters per second. Then you need to get the period. And if you go from point A to point D here, that's 2 periods. And D here is at 2.218 seconds. A is at 0.018 seconds. So the period, or 2 times the period, is 0.2. And the period itself would be 0.1 seconds. And if you know the period, you always know the angular frequency, and that's going to equal 2 pi divided by the period, or 2 pi divided by 0.1, which is going to be equal to 20 times pi. Next, you'd like to get the phase angle. An unshifted cosine function would have its peak at t equal to 0. So we're getting shifted to the right. And that means our phi angle would be negative for a shift to the right by 0.018 seconds. So we're shifted right, which means our phi would be negative, by t equals 0.018 seconds. So to find the phase angle, we know that t divided by the period must equal phi divided by 2 pi. So our phi value is going to equal 2 pi times 0.018 divided by 0.1, which is going to be, and remember, this has got to be a negative value, negative 0.36 times pi. Now, if we wanted to express it as a positive value, and there might be a reason for doing that, then as a positive value for phi would just be 2 pi minus 0.36 pi. And if you do that, of course, you're going to get 1.64 times pi. So our equation is going to be V equals V0 cosine omega t plus phi. So V0 we said was 5. Cosine omega was 20 pi times t. And then we'd either write here minus 0.36 pi, or alternatively plus 1.64 pi. And you might want to check that answer out. So for instance, if I take, say, my time equal to 0.25, then my velocity should be somewhere around negative 2.1, negative 2.2. And if I plug my numbers in there, 5 times the cosine of 20 pi times 0.25 for the time, say minus 0.36 pi, I get an answer there of negative 2.13, which agrees with what the graph says. In this question, we're given some physical parameters and an initial condition, and we're asked to find the mathematical equation, the displacement time equation, as a sine function. So pause the video, try the question, come back to the answer. Well, let's start by writing what we've got. We know the amplitude, so we know that x naught is 5 centimeters. We can figure out the period because that's given by 2 pi m over k for a mass spring system, so that's going to be 2 pi. M is equal to 12, and our spring constant is 24. So if we plug that in and work it out, we get a period of 4.44 seconds. So our angular frequency will be 2 pi divided by the period, or 2 pi divided by 4.44. And if we plug that in, we get 1.41 seconds to the minus 1 for the angular frequency. So that gives us this much of our equation. We know that x should equal x0 sine omega t plus phi. We know that the x naught is 5. We know that the omega is 1.41. We don't know the phi yet. So we have this much. We can now use this other bit of information that at t equals 0, the displacement is 2. So we could say that 2 would equal 5 times the sine of 1.41, and we take the time to be 0, which means that we get that the sine of phi must be equal to 2/5. And we can work out what our angle phi is. It's just going to be the inverse sine of 0.4, which is 0.412. So we can come to this equation and write that our equation for the simple harmonic motion of our mass spring system will be 5 times the sine of 1.41 t plus phi, which is 0.412. So there is our equation. So here's a final example. Pause the video, read over the question, try it out, come back for the answer. So the period is simply going to be the time to reach that crest again, so that's going to be 10 seconds. And since we've got the period, we might as well get the angular frequency as well. That's 2 pi divided by the period, or 2 pi over 10, which is 0.2 times pi. In part B, we want the amplitude. That's simply going to be 6 centimeters. C, we want the maximum speed. The maximum speed is given by the angular frequency times the amplitude. So we're going to have 0.2 pi times 6, or 1.2 times pi. Or D, maximum acceleration is given by angular frequency squared times the amplitude, which is going to be 0.2 pi all squared times 6, and that's going to come out to be 0.24 pi squared. So we can now write our equations. The displacement will be equal to the amplitude 6. We're going to write it as a sine function. We could write it as a cosine function. I'm going to write it as a sine function with a phase difference. So we'll have a sine omega was 0.2 pi times t. And then we've got to figure out what that phase shift is. If we had a sine function, it would look like this, and we've got to shift that backwards by a quarter of a period. So our phase angle has to be a quarter of a period, a quarter of 2 pi, and of course a quarter of 2 pi is pi over 2. So we add on pi over 2 here. Our V would equal V max, which we said was 1.2 pi. It's going to be a cosine function, and the argument will be the same. And our acceleration will equal the maximum acceleration, 0.24 pi squared. It's going to be the negative sine function. Acceleration and displacement are always in opposite directions. Of course, the argument's the same. So we get these three equations. And then in part F, what we want to do is simply plug in to these equations. Plug in t equal to 6 seconds. And if you do that for x, you should find that you get negative 0.485. And you can see that on the graph right here. That seems to be at about negative 0.485. Our velocity comes out to be 2.21, and our acceleration comes out to be 1.91. And it's a good idea to kind of check to see if this is working out physically. So if this is your equilibrium position, you're talking about an object displaced to the left by 4.85. It's moving to the right since its velocity is positive, so it's moving to the right at 2.21. And if it's moving to the right and to the left of equilibrium, its acceleration is also going to be to the right. So its acceleration should also be positive, 1.91. So everything seems to be consistent there. Okay, let's summarize the big ideas in the video. So we said that the equation for the displacement would be given by the amplitude, and then we always write the trig function as a sine, and we include a phase angle. The equation for the velocity then would be given by the maximum velocity. It will go as a cosine, and the argument will be the same. This maximum velocity here can be written in terms of the angular frequency times the amplitude. And then the acceleration will be a negative sine function because the acceleration and displacement always have to be in opposite directions. So we'd have a maximum acceleration here. This will be a sine function, and of course the same argument. This maximum acceleration can be written as the angular frequency squared times the amplitude. Now this phase angle is related to a shift of our curve. It's given by t over the period times 2 pi, where this t here, if we think about our graph, and this is what the graph of sine omega t would look like. But we can always think of our actual data equation as being a shift of the original equation sine omega t. So you can see here that the sine omega t got shifted to the left a certain amount backwards to the left. So t is the amount of time shift to go from sine omega t to this sine omega t plus phi. And keep in mind here, the phi is greater than 0 if we shift left, and it's less than 0 if we shift right.
I know it's in your best interest not to tell others about this channel because it gives you an unfair advantage. But could you like, subscribe, and sign up for notifications anyways?
And that's all for today, folks. Thank you very much.